I'm going to do these by hand, but I'm going to show you how to do them in your calculator as well. So we're taking 3 times 5 to the negative first power, evaluating that. We're taking 3 times 5 to the second power, evaluating that. And we're taking 3 times 5 to the third power, evaluating that. A negative power, remember, is reciprocal. So this is like 3 times 1/5. So 3 times 1/5 is 3/5. This one right here is you have to square it first. PEMDAS, you got to do exponents before multiplication. Do not do 15 and then square that. If you do 15 squared, that is absolutely wrong. You got to take 3 times 25, which comes out to 75. And then here, again, you got to do the exponent first. So that's 125 if you cube 5, 5 times 5 times 5. And if you multiply that by 3, you get, 125 times 2 is 250, and so one more would give you 375. So this would be 375. Now, a nicer way to organize this is in a table. So if you want, you could have here the x's and the y, which the y follows the rule. You take the x, right, and it becomes an exponent on that 5, and then you multiply that result by 3. So when x is -1, you get 3/5. When x is 2, you get 75. When x is 3, you get 375. This is having those same answers in table form, and you can actually do that in your calculator as well. You can use a table to help you evaluate these quicker. 3 times 5 to the x, plug that in, and you go to second graph, which is like second table. And if you notice, if I plug in -1, it outputs 0.6, which 0.6 is 3/5. And then if I plug in the other exponents, if I plug in 2, I get 75. I plug in 3, you get 375. But I have my table set up here, if you go to second table set, to ask for values instead of just listing them out 1, 2, 3, 4. I can list them in any order I want. So I can even evaluate this function when x is equal to 5, and it'll give me that. I can raise it to even like really high powers, like, like 13, and it's going to start giving me really big numbers in scientific notation. But these are easy enough to do by hand, but you can use your calculator to evaluate those. And you can also just enter them in your home screen calculator. But just remember order of operations. For number 15, again, we're still evaluating those with the same powers. Now, these are in function notation. So if you evaluate it when x is -1, I'm going to replace this x with -1. And so I'm also going to replace in the rule, I'm going to replace this x with -1. Negative power, again, is reciprocal, so that's the 1/2 is there. The reciprocal of 4 is 1/4, so you get 1/8 as the answer. So if we evaluate this when x is 2, and the way we read this is f of 2, but we're just substituting, changing the x with the 2. So we change the x on the other side with a 2. Order of operations, first square the 4 and get a 16. And then half of 16 is going to be an 8. So the function evaluated at 2 is equal to 8. Lastly, if we replace the x with a 3, f of 3, this is not read as f times 3, it's f of 3. First, we raise the 4 to the third power. That's 64, and then we do half of 64. So this function evaluated at 3 comes out to 32. But this is just getting practice evaluating functions. Last one where we're just evaluating is 16. And this is really where you want to use a calculator because these decimals get kind of hard to deal with when you're raising them to higher and higher powers. So evaluate this function at -1. And so we're just replacing this with x. But I'm going to lean on my calculator here because it's a lot more efficient in doing these. You can do it in your home screen if you're not really comfortable using the y equals in the table. You can just enter it right here on your home screen. 4 times 0.95 to the power of x, but the power of x is at first going to be -1. So your first answer is, you could just round this off to, I'll specify how many decimal places to round off to. But usually when we're dealing with these sort of exponential models, we're dealing with money. So it makes sense to round to two decimal places. Instead of retyping that, I want to evaluate that when x is equal to 2. So I'm just going to walk up here, change that -1 to a 2, and delete the stuff I don't need. And so we got that right there, 3.61. Walk up here, go over to that 2 exponent, change it to a 3. Notice how these are your answers, right? And that's if I use my home screen to do that. The home screen is just that default screen. But I can also do this. I'm going to put the 0 this time just because I like the way it looks. I can use that table function, and I'd like you to eventually get comfortable using the technology. I can go to my table, okay, and let me just delete these values out. Evaluated at -1, and guess what? I get that answer I got on the home screen. Evaluated at 2, evaluated when x is 3. And so it very quickly gives me those values without having to retype it or rechange it. I just give it the x and it outputs the answer right away. So it's really nice being able to do this using the table. But either way, these are your three answers. And we're using these values as sort of like a precursor to figure out how to graph these things. Because if you can graph it, the y value at any given x value, you can sketch what those graphs are going to look like. And just as a little key in case you want to set your table up to do that, if you hit second and you hit the window key and you set your table up this way, that allows you to just customize and put in the values, put in only the x values that you want to put in there. You get that second window, second table set. That's why it says table setup. And then second graph, second the table blue button is how you get to the table itself and actually enter those values in. Now, the reason we were evaluating that function at different x values was really so we can start to learn what the graph is going to look like. So I can graph this like it's not a slope intercept form, so it's really hard to graph it intuitively by just plotting y-intercepts and any of that because it's not in slope intercept form. But if I use a table and I can do it by hand first, so y equals 1/2 times 2 to the x. If I start with let's start with x equals 0. When x is 0, well, I have 1/2 times 2 to the 0. 2 to the 0 is 1, so when x is 0, the y value is 1/2 times 1. So we can plot right there. It's not that hard to plot 1/2. I mean, you just go between the 0 and the 1, right? Now, when x is 1, we get 1/2 times 2 to the first. That's 2 times 1/2, which gives you 1. So when x is 1, y is 1. And then you might think it's going to be a line. It will not be. This is an exponential function. Keep plotting a few more points. 1/2 times 2 to the second. Again, we're just replacing the x with whatever the x value we're given is. 2 squared is 4. 4 times 1/2 is 2. So when x is 2, the y is 2. But now you can start to see it change. Notice how this thing is doubling based on x. And even if you don't see that, just use the table. 1/2 times 2 to the third. 2 to the third is 8. 8 times 1/2 is 4. So when x is 3, the y is 4. Let's do one more. But after this, we're going to start to go off the grid. 1/2 times 2 to the fourth. 2 to the fourth is 16. 16 times 1/2 is 8. So when x is 4, the y value is 8. So this is your function, your exponential function right here. But what does it do at negative values? Well, plot at least two negative values so you can start to see it. If you take 1/2 times 2 to the negative first power, you'll notice that this is 1/2 times the reciprocal here is 1/2. You actually get 1/4. The idea is you get a really small number, but no matter how far you go, you'll never end up with negative y values. Again, there's a lot of strength in being able to do this in your calculator. Now, I like decimals just fine, so if I do 0.5 instead of 1/2, times 2 to the x. That'll give me decimals. If you use alpha y equals and enter it as you see, and you put like 1/2 times 2 to the x, notice that these are the same thing, but when I go to graph them in my tables, and I already know that, look, the positive values are actually giving me exactly what I did if I did them by hand. So there's a lot of usefulness in being able to do this in the calculator. Notice how once you go past 5, the x value 5, you start going off the grid. So we wouldn't even be able to plot it anyway. So it just kind of like at the x value 5, this thing just explodes and goes off the grid. Let's look at the negative values. We haven't seen what the negative values do. -1, all right, we saw that this was 1/4. That's where that came from. Let's look at -2 and -3 and -4. Go back here, retype that -3 and -5. No matter how far negative I go, notice how these answers are not negative. The answers are just really tiny, tiny numbers. So exponential functions, they just tend to like hug the x-axis here. So I'm really exaggerating how far it is right here. It's actually gonna, to your naked eye, it's gonna look like it actually like goes on top of the x-axis. It's gonna look more like that, more so than the first one. It'll look like it just goes on top of the x-axis. So if I just graph like that far right there, and I'm being careful not to go below the x-axis, so even though I'm a little bit higher than I need to be, the idea is that this thing just like bottoms out. You'll learn in other maths that this is called an asymptote. That's spelled Asymptote, but you don't have to know that, so I'm going to erase that. You can do some more reading on your own about that, but the idea is it hugs the x-axis for these negative x values. And this is exponential growth. And even more specifically, this is a change. This is an increase by 100%. This is, yes, it's a growth factor of 2, but if you want to know it as a percentage increase, you subtract 1 from your growth factor. This is a 100% increase. That's how we go from 2 to 4, 4 to 8. So you're increasing by all of what you had the previous X step or the previous time value or year, if this was years. From 1 year to the next, you double in value, so you increase by 100%. But this is the graph of that function. For 18, again, we're graphing this, and I'm going to do this in red ink instead. But it's highly advised that you just use a table to do that. If you want to know how to graph it more intuitively, I mean, you could see that if you put a 0 right here, that raises whatever this growth factor is to the 0 power. So it actually becomes like, this just cancels out to a 1, so you get 2 times 1. So your y-intercept of an exponential function is actually always what this initial value is. So it's always going to be that 2. So, and then the idea is we're decaying, which should be obvious because the growth factor is less than 1. You're decaying because you always have half of what you had the previous year. So if I want to graph it, I have half. I started at 2. Next year, I'm at half of that. I'm at 1. Then I'm at half of that, so I go from 1 to a half. Then I go to half of that. Half of a half is a fourth. And then it just starts disappearing and decaying. So you get this sort of image right there. All right. Now, to go negative time values, I'm going to show you the actual table values in a second. But if each year I go forward, I decay by, this is really a 50% loss. And the reason it's a 50% loss is if you take 1/2 and you subtract 1, you get -1/2, which is equal to -0.5. That's why it's a 50% decrease each year. So for instance, if it was 2 times 0.7 to the x, this is not a 70% decrease. If you take 0.7 minus 1, you get 0.3 negative. That would be a negative 30% decrease, okay? But if I go forward in time, I get cut in half. That means if I go backwards in time, that I'm going to be doubled. So I'm guessing that my -1 value, when x is -1, I'm probably going to be at a y value of 4. When x is -2, I'm probably going to be at a y value of 8. And then if x is -3, I'll be at a y value probably of 16. but I'm guessing this is what my function would do that. I don't have to guess. You can use your calculator to start sort of evaluating those exact values. You can use a table if you want, or you can do it in your home screen. Sure enough, if I raise 2 times 1/2, if I do 2 times 1/2 to the negative 1, yeah, you get 4. And if I do 2 times 1/2 and then raise that to the negative 2, sure enough, I expect to get 8. So if you didn't click, like how I was able to, like, what do you mean double if you go backward in time? Again, just use your calculator, or you can plug it into your y equals. Now you can also just graph this, and I can type the 1/2 by doing 1/2 like that and raising to the power of x, or I can type it as 0.5, and you actually don't need that multiplication sign because it's applied. You could do alpha y equals, and you could type 1/2 like this. Now here's what graphing on your calculator doesn't do. It doesn't translate it from your calculator to your paper, so you still have to be able to figure out how to get it from that graph to these paper values. And I expect you to plot very clear points, at least like 4 to 5, more likely 5 clear points. But what I'm going to do is I'm going to graph both of these just to show you that they're the same thing. I'm going to graph one of them thick. And I'm going to graph in the standard window. Hit zoom, option 6. There's the first graph. And actually, it's going to graph it again, but thicker. So they're both the same line. And even though it appears like it goes below the x-axis, it doesn't. There's an artificial thickness to that line. But so great, your calculator can graph it, but you still have to be able to put it onto paper. Doing it in the home screen helps you get those points a lot more clearly, or going to your table and, plotting like -3, -2, -1. These are some of the best x values to put in. You want to put it always in at least a couple negatives and a couple of positives, and they could be returned as decimals or fractions, whatever is most convenient for you. But that's how to graph these exponential functions by plotting, just plotting 1 or 2 points at a time until you get at least like 5 points. Like here I have 1, 2, 3, 4, 5, 6. I have 7 points, but you want at least 4 to 5 points so you can see that curve. You don't want to assume that this is a line. It is not a line, it's an exponential function. Okay, now we're getting into the application of these exponential functions. You should be able to read this question and understand how to model this. So the general formula for this is we take a principal amount that's invested or borrowed, depending on the situation, and we do 1 plus, because you keep what you had and then you change by a certain percentage, r divided by how many times you're going to compound that. And then over here for the exponent, you're going to be taking that number of times that you compounded times how many years pass. Now, because this thing is compounded quarterly, that means that it's compounded 4 times a year. So I'm going to do the amount is equal to the principal that's invested, which is 2,000. Okay. And then it's going to be 1 plus, well, what is the R? The R would be 5.2%, but we want to convert that to a decimal. Remember, you move the decimal place 2 places over. So that's 0.052. It's optional if you want to put this preceding 0, but you do have to put this one right here. So it's going to be 0.052. That's if I don't put the 0 in front. And then we compound that 4 times. And then at first we want to see how much is in the account after 2 years. We compound it 4 times for 2 years. Since we compound it 4 times each year, okay, that means we're compound 8 times. That's where this 8 comes from. I like to just leave it as 4 times 2 though. But at this point, you could just run this into your calculator. Now, let's say, for instance, that it wasn't quarterly. Let's say that it was just annual. All right. If you just compounded this thing annually, well, you wouldn't have this 4. That would just be a 1 because you only do it once a year. And you wouldn't have this 4, and that would be a 1 there. So if it was done annually, you just have 1s there instead of 4 there. And really, the number isn't going to be that much different, but Let's do it both ways. 2,000 times 1 plus, and I'm going to do alpha y equals because I like the way it looks. So I'm going to take 0.052 over 4, and then I'm going to raise that to the power of, instead of putting like an 8, I'm going to actually put 4 times 2 because the calculator can handle it just fine. This is if I compound it quarterly, so you get about, at the end of 2 years, you get $2,217, and well, we got money, so it makes sense to round to 2 decimal places. So you get 17 cents. Now, if I did this annually, again, there's not really a need to put the ones at all. Like they could be invisible if you want to. But I just want to show you that there's a little bit of a difference between compounding it annually and compounding it, in different methods. But notice how it's not that much of a difference. It's a difference of, about $4. So they only ask quarterly, but this is just me showing you the difference. So after 2 years, you get basically approximately $2,217.71. All right, and it's really close if you do it annually. Now, let's do it not just after 2 years, let's do it after 5 years. You can retype this if you want, but again, let's go to the quarterly one that we already did. Instead of retyping it all, that 4 is because of the quarterly, so don't change that. Change the 2 years to 5 years, so change this 2 to a 5. And after 5 years, the money that we invested at a 5.2% interest rate, compounded quarterly 4 times a year for 5 years, if you invested $2,000, would be equal to this. So this is the amount compounded quarterly after 5 years. And just as a comparison, let's do it just annually after 5 years. Again, you get a number that's relatively close, but the further along in time you go, notice how they were spaced out by about $4 before. Here they're spaced out, a lot more. So now they're spaced out closer to like $13 or so. So compounding more times a year results in, if it's an investment, that's an advantage for you. If you're paying debt on something, so like if you're paying off a credit card, they compound those daily. So that's kind of a drawback for you. But whoever is the person generating the interest gains a little bit more if you compound it more times a year. So compounding it monthly generates more interest than yearly, which is annually. And if you compounded it daily, this would be like 365. That generates even better interest. But there are these tiny little fluctuations over the short term, but over the long term, it can add up to a lot. So $2,217.71 is the answer for the first question, and then $2,589, and let's round up to 52 cents here. That's the answer to the part asking after 5 years, and that's compounded. All right, some more practice with exponential functions. This time, instead of growth generating interest, we're dealing with decay. We know we're dealing with decay because this number is less than 1. So this is depreciating in value. It's lowering. That's what depreciating means. That's what it means. The decay factor, okay, decay factor is 0.85. But what does it mean? A 0.85 decay factor, if we take 0.85 and we subtract 1, we get negative 0.15. Now, here's what that means. This means a 15% decrease in value each year. So this is you're decreasing by 15%. You're not increasing by 15%. And here's what's important. You are not decaying by 85%. That's not how this works. The idea is each year you have 85% of what you had the previous year. So if you have 85% of what you had, that means you have 15% less than what you had. So that's part A. Now for part B, we want to know the car's value after 1 year. Well, we're given the function, so x represents the number of years, so we just evaluate that function. So you could calculate it but we're going to change that x to a 1. So I'm going to type 30,000, and don't use commas. Your calculator doesn't like when you use commas and numbers. It won't accept that. Times 0.85 raised to the power of 1. Now, I want to show you something. This is the answer, but guess what else? If I took 30,000 and I multiplied it by 15%, okay? I'm arguing that this is you lose 15% each year. If I take 30,000 and subtract what 15% of 30,000 is, notice how I get the same answer? So that's my evidence that this is you lose 15% each year, even though it's a UC of 0.85. So after 1 year, you're going to have a value of $25,500. Now, let's calculate the value after 4 years. Well, we're given the model. Since 4 years, x represents years, so let's just replace that exponent x with a 4. So I can scroll up, since I calculated it here with an exponent of 1. Instead of retyping it, I can just go over here, change that exponent to a 4. I expect it to be, since it goes down less and less each year, there I go. I expect it to be a lot less than 25,000. So it's instead of 25,000, it's about 15,000. It makes sense to round to 2 decimal places because we're dealing with money. So this much in dollars and then 19 cents. So you get this as your value, and this is the value of the car after 4 years. And that's the answer for number 20. For number 21, we're trying to point out the error here. Here's what they did wrong, okay? Can you see it? They're supposed to add the exponents, so this is good. The 7th power is good, but you don't multiply the bases. 3 to the 4th times 3 to the 3rd is 3 to the 7th. You can confirm it in your calculator. If I do 3 to the 4th times 3 to the 3rd, I get this 4-digit number. If I do 3 to the 7th, I get that same 4-digit number. If I try to do 9 to the 7th, I get a much different, bigger number. So it does not work. Like you should add the exponents. They did that right, but you're not supposed to multiply the bases here when they're the same base. That is wrong. For 22, we're showing that these expressions are the same, and we're going to rewrite this in exponential form. Well, what is a third root or a cube root? Well, we know that something cube rooted is the same thing as that thing to the 1/3 power. So since I have x to the 9th and it's cube rooted, that's the same thing as x to the 9th to the 1/3 power. We know that when you raise a power to a power, you multiply the powers. So it's x to the 9 times 1/3. 9 times 1/3, sure enough, is 3. So that's x to the 3rd. Now, if you want to leave it in radical form, this might be something that you don't know yet. But x to the 9th and 3, you can kind of like divide the powers. When you study more radicals in Algebra 2, you'll be doing more of that. But it's enough to just see that if you write it in radical form, raising a power to a power, you get simplified x to the 9th cube rooted is actually x to the 3rd or x cubed. For number 23, they want us to be able to tell when we have exponential growth versus when we have exponential decay. Now, do you remember what qualifies exponential growth and decay? If you forget, I would highly suggest taking a look back at numbers 19 and 20. One of those was growth and one of those was decay. And where's the rule. If you have like y equals, let me just choose a number for a, let's say 100. You do 100 times 1.07 to the x. This is a 7% increase. This is growth. But if you had y equals 100 times 0.93 to the x, that's a 7% decrease. So here's the idea. You have growth when your growth factor is bigger than 1, the b, when the thing you're raising to the power of x, or you can raise it to the power of t. Some people use t for a time variable. This is growth. When your growth factor is bigger than 1. When your growth factor is less than 1, it's not negative. It's less than 1. That's exponential decay. And you can refer to numbers 18 and 19 for clear examples. Actually, not 18 and 19, but 19 and 20. 19 was growth, growing in an investment, and 20 was decaying, depreciation of value of a car. For number 24, let's do this in two different ways. So here's one way you can do this, okay? First, you can work what's inside the parentheses and simplify those first. A to the 6th divided by A to the 4th. The shortcut is to take 6 minus 4, okay? And then we'll deal with that power of 2 here later. Oh, that's A squared. All right, then we have A squared raised to the second power. So you multiply the powers, you get A to the 4th. Here's the other way to do it. Instead of working what's in parentheses first, you could have distributed that exponent to the top and the bottom here. So you would get A, 6 times 2 is 12. On the bottom, A, 2 times 4 is 8. And then we could subtract later. So A to the 12 minus 8. So you still get A to the 4th. So that's two ways to work number 20. Okay, the last one on the study guide, we want to explain how you can use the property for dividing powers with the same base to justify the definition of a zero exponent. Now, when we first covered it, we saw that 2 to the third is 8, 2 to the second is 4, 2 to the first is 2, 2 to the 0 is 1, okay? And then we were just dividing by 2 each time. 2 to the negative 1 is 1/2. So we saw a pattern, but here's how you can use the property of dividing powers. All right, let's look at 2 to the 4th over 2 to the 3rd. All right, that cancels out if you subtract the powers, 2 to the 1st. If it's 2 to the 70th over 2 to the 68th, 68 of the 2's will cancel out. If you expand them out, you get 2 to the 2nd. You subtract the powers. Well, what if you have the same power on the top and the bottom? Say you have 2 to the 3rd over 2 to the 3rd. We know that when you're dividing two powers that have the same base, 2 to the 3 minus 3. All right, so if you did the shortcut, you get 2 to the 0, but what is 2 to the 0? Or if you're dividing a number by itself, we know that 2 to the 3rd is 8, and this is also 8. 8 divided by 8 is 1. So that's a way to convince yourself that something to the 0 power is 1, and it doesn't have to be with the number 2. It could be with any number. If you take 7 to the 40th power over 7 to the 40th power. I have no idea what 7 to the 40th power is, but I know that any number divided by itself is 1. I know that the shortcut rule for dividing powers that have the same base is you subtract the exponents. So this is 7 to the 0, but because you divide it by itself, it's 1. So I have convincing evidence that something to the 0 power is always equal to 1. And that's the end of the study guide for Chapter 7.